So I would have to take a longer look at this, and I have to get to the next tutorial. This one will take a while, but what I would suggest is please don't use this. We have to learn how to take sums, because on the test, you might be asked to take a sum without using the fundamental theorem of calculus. Right? So you have to be able to know how to do that. Thank you. Bye. Okay? Constraint is just any equation that we're given in the question. So, for example, here, when we're told that the surface area has to be 4,000 centimeters, this is our constraint. That is our constraint. Yes. No, that is not correct. So, if you take, you cannot take, like the integral of the product is not the same as the product of the integrals. The way you can show that this solution is wrong is take the derivative of this. Take the derivative of this, you will not get this back. You have to do it the way we did it. This is the, so look, we found, we said, how do we get f from f prime? We found f here. If you take the derivative of f, it should give you f prime back, right? But if you take the derivative of this, it will not give you f prime back. Because you need a product rule here. Thanks. Hey, how's it going? Yeah, that's okay. What I was doing was writing y as a function of x, because we know if we have that this point is lying on the triangle, we have an equation for y as a function of x. Now, you know what? I'm sorry, it's 2:30 now. I've got to run to the next tutorial. But for everyone else, feel free to send me an email, and I'll respond. I'm watching the next tutorial again. Oh, you're gonna come? Okay, so maybe we'll see it one more time. Okay. Good stuff. Yeah. Yes, send me an email if you can. Sorry, we're just about to start the next tutorial.
Thank you.
Hey, how's it going? Alrighty, let's get started. Let's get started. So. All right, let's get started. Let's get started. So, how is everyone doing today? Doing good? Woo! I'm very glad to hear that. So, everyone have a good reading week, a good happy Thanksgiving? Very nice. I'm so glad to hear that. For myself, I went back to Toronto, or Etobicoke, if you know where that is. Spent some time with the family, with my sister, and yeah, it was a good time. So the next question is, how did everyone find the first test? Did it go good? Maybe not as good, not so good, or maybe not like what we would expect? That's okay. The first thing I want to say is, if the test didn't go as well as you expected, that's okay. This is our first round of midterms, probably the first tests that we've ever taken in university, right? These tests are a lot different than what we have experienced before, and the types of questions are a lot different than what we've experienced before. The point of being here at all is just to try and learn as much as we can. And my goal is to try and help us all understand where did we go wrong, how can we try and improve upon any mistakes, and be the best that we can. So first and foremost, that's okay. If you have questions about the test, I've posted a take-up video. I've taken up every question on the test. At the very least, please watch it for every question that you got wrong. I know it's a little bit painful. I don't like doing this myself, but if you got any test questions wrong, please watch the solution, because if you don't, when that question appears again on the final, you also won't know how to do it. Okay. Midterm survey, I also posted that on Teams for anyone who didn't get a chance to fill it out before the break is over. Just helps me better understand, you know, how to give you guys the best experience I can. A lot of people had said so far, they said, where did the candy go? So I have lollipops today. Also, before I forget, next week is Halloween during tutorial. So please wear your costumes. I'm going to wear a costume on the day of. And there will be better candy than lollipops. I'll bring some chocolates or something. So, alrighty. So, alrighty, so today, this week, we're going to cover derivative applications. So in particular, optimization, finding a function given its derivative, and we're going to look at summation, telescoping series, and Gauss's trick. Now in the last tutorial, we didn't get a chance to finish all of that, so we might move some summation stuff to next week. Alrighty. Alrighty, let's get started. So Ibrahim, is Ibrahim here? Not in the last tutorial either. Okay, so Ibrahim has a cat named Bebzi. To make a cat house for Bebzi outdoors, they have 1,000 centimeters of fence. They decide that the fence should have a border around each side, and there should also be a fence in the middle to split the pen into 2 equal halves. The question says, what side lengths would maximize the area of this pen? So let's really quickly make a drawing of what this looks like. We have this rectangular pen here. We're going to split it into 2 halves by this piece of fence here. And we'll let x be this distance right here, and y be this vertical distance right here. Okay, before we proceed, I want to talk about a general framework for optimization problems, because these can be tricky, especially converting down of our word problems into equations of multiple variables into something we know how to solve can be very tricky. So let's do it in a flow chart. Here's our flow chart. Step 1. Actually, let me just sync this with what we did last time, because I don't remember what. I just want to make the steps the same. So in step 1, we said we're going to model the real-world equations, model the real-world scenario using equations. Then number 2, we're going to identify the objective and constraint. And I'll talk about what that means in a second. Number 3 says we are going to create a single variable objective. By substituting the constraint. And number 4 says we are going to maximize our single variable objective. Okay, so let's talk about what this means. What does this mean? So let's do step 1 together. We're going to model our real-world scenario using our equations. So in particular, we know that the area of this pen is, well, what's the area of this pen? We have side lengths x and y. It's a rectangle, so what's the area? xy. Very good. And also, we have a constraint. We know that the perimeter of this, which is equal, or not the perimeter, sorry, just actually 2x plus 3y, which is the total amount of fence we have, that equals 1,000 centimeters. Okay, one of these is our objective, and one of these is our constraint. Can you tell which is which? Which one is which? Let's see. Yeah. Yes, the objective is the area function. So the objective is what we're actually trying to maximize. So this is our objective, the area. Now, notice our objective function is a function of two variables. We don't yet have the tools in our toolbox to do calculus on two variable functions. That'll be next semester in 1ZB3 and your third course in calculus, it'll be 2ZZ3. Anyways, that's our multivariable calculus. We'll get to that later. For now, we need to turn our multivariable function into a single variable function. How do we do that? We substitute our constraint. So we're going to let y equal 1,000 minus 2x over 3. Now we've written one of our variables in terms of the other. We can substitute it back into our objective. So now we can write a as a function of x by writing x times 1,000 minus 2x over 3. So now we've done step 3. In particular, we want to maximize a now. So before we continue, is everyone okay with how we set up our problem? So now we want to maximize this single variable function. In particular, what shape does this function have? Sorry? Oh no. Yeah? Yes. What shape is A? A has something we know. It starts with a P or a Q. Yeah? Parabola, yes, it's a quadratic, a downward-facing parabola. That means it has only a single maximum, in fact, at the vertex of the parabola. Let's find that vertex. So a prime of x is going to be product rule 1,000 minus 2x over 3 plus x times negative 2 over 3. The other thing is, because we've been doing derivatives so long, I'm going to spend less time working out derivatives and spend more time on setting up the problems and computing. Is that okay? Is that preferred, or do you want me to go through the derivatives? Prefer more focus on the problems. So now that we've computed this derivative, let's search for the critical numbers by setting the derivative equal to 0. So a prime of x is equal to 0. So that tells us that 1,000, let's multiply both sides by 3. So 1,000 minus 2x is equal to 3. So, is equal to 0. So in that case, x is equal to 1,000 over 4, which is 250. Okay, so are we done? Oh, yeah.
When you took the derivative, don't you have to turn that 3 into 9 using quotient rule?
Turn that 3, I'm not using quotient rule, I'm using product rule here. Because we're taking derivative of x times, oh, I see what you're saying. Where are we using quotient rule?
For the 1,000 minus 2x over 3.
Yeah, the derivative of 1,000 minus 2x over 3, that's a line, right? So the derivative of a line is the slope of the line, which is negative 2/3. Yeah. So from here, we set our objective function's derivative equals to 0. We solve for x, that gives us 250. So are we done? No, what do we need to find now? I heard it. What, sorry? Y, yes. The question asked what side lengths. So we need the other side length. So y is equal to, so here, this is part of our solution. Y is equal to 1,000 minus 2 times 250 over 3, which is equal to 500 over 3. And that is our final answer for y. Okay, so what questions do we have about this first one? Is everyone okay with our, oh yeah.
In this case, we know that it wouldn't be the situation, but don't we have to sometimes check the maximum constraint and minimum?
Yes, yes. So the question was, don't we ever have to check the constraints? In general, you do. Here we definitely don't, because we know our objective function is a downward-facing parabola. Its only maximum occurs at its vertex. If we were to check the constraints, well, we know our side length x and y have to be bigger or equal to 0 because they're distances in the real world. If either of x and y were equal to 0, what would be the area of the pen? Shout it louder. What's the area of the pen? 0. So we know that either of those constraints are not going to be maximums of this area of this pen. Alrighty, so let's take a look at question 2 here. So Joelle is a lifeguard and wants to practice running and swimming to save someone. To do so, Joelle crosses a river and runs to a point on the opposite side of the bank. The river is 150 meters wide, and the point to be reached is 5,065 meters downstream. Okay, these types of questions are really have a lot of stuff in them. So let's do it together. So Joelle is going to start here and end here. This distance is 5,065 meters downstream. So this length is 5,065 meters. The river is 150 meters wide. What's going to happen is Joelle is going to swim to a point on the opposite bank. And then Joelle is going to run parallel to the river. Okay, let's set up some variables here. Is everyone comfortable with how we've defined all of these problems so far, this drawing? This is our real-world modeling of the scenario. Let's look at the point on the opposite bank. That's what we're trying to solve for here. The point on the opposite bank, we'll call it x. In this case, this region here, that's 5,065 minus x. And this orange distance here, how far is that? Well, by our Pythagorean theorem, this is going to be the square root of 150 squared plus x squared. And in that case, now we can start writing our objective and our constraint. Actually, we don't even need a constraint here because our objective function tells us enough information because we only have a single variable. Okay, so how are we going to do this? Let's minimize the travel time. So how do we solve for time? Well, we remember from our physics classes, velocity is equal to what over what? So, one more time? Distance over time. So if we're solving for time, that gives us that time is our distance divided by our velocity. In that case, we can write time as a function of x by deciding the distance that we have to travel. So this distance here is root of 150 squared plus x squared divided by, we have our swimming velocity is 2 meters a second. Plus, we have this horizontal distance we have to run, 5065 minus x, and we have that our running distance, our running speed, is 5 meters a second. And our goal is to optimize t. Let's take a really quick pause. Is everyone okay with the problem statement now? Okay. So in particular, let's solve this one. So to find a maximum, let's take the derivative and search for the critical numbers. T prime of x is going to be equal to, now let's take this derivative, we have a square root, so that's going to turn into 2 times, power rule, 2 times, root of 150 squared plus x, chain rule 2x. So our 2's are going to cancel. Next, we're going to take the derivative of this line. That's just the slope of the line, so minus 1/5. And to search for the critical numbers, we're going to set our derivative equal to 0. So in that case, we can solve by cross-multiplying. So we have, well, let's write it one more time. X over 2 times 150 squared plus x squared is equal to 1/5. So if we cross-multiply, that'll give us 5x is equal to 2 root of 150 squared plus x squared. In that case, we can square both sides. 25 squared, x squared, is equal to 4 root of 150 squared plus x, 150 plus x squared. So we can expand 4 times 150 squared plus 4x squared. So 21x squared is 4 times 150 squared. So x is equal to 4 times 150 squared over 21 square rooted. Now we square rooted both sides, so do we need a plus or minus? Who says we need a plus or minus? Why do we need a plus or minus? Yes. X cannot be negative distant. Well, I guess in theory, actually, I changed my mind. I guess in theory it could be, but it won't be because we know we have to just run farther. So no, it's just one solution for x here. Alrighty. Cool. What questions do we have about this one? Oh, yes.
Shouldn't it just be 5 squared? Because you wrote 25 squared, but isn't 25 5 squared?
Aye, very good. That should be 25. Thank you. 25. And does that change any of the math? It's fine. I was treating it as if it was 25. That's fine. Because 25 minus 4 is still 21. So good catch, though. Thank you for catching that. You have a question here as well? Yeah. Oh, same thing? OK, very good. Good catch. If I ever miss something while I'm writing, if I'm looking down, just shout at me. I'm very casual. Yes?
Well, the only thing I have to do after this is just sub x into the time equation, then you get the answer, right? Or you have to check if it's a minimum?
So I guess in theory you should check it's a minimum. You could do that by using our second derivative test from 2 weeks ago. So we can check that the second derivative of that is going to be positive, so we have a concave up function, so we know it's minimum. So absolutely, that's going to be your homework exercise right now. No, we don't need to sub it back in because it's asking for a point. So we need x. We don't need t. So we don't need the actual minimum travel time. We just need the point. Alrighty. Is Karina here? Okay, so Karina likes to make ceramics, and using 4,000 centimeters squared of material, wants to design a bowl which has the largest volume. Assuming the bowl is a cylinder without a top face, what is the maximum volume? So let's do the exact same problem setup that we did before. Our cylinder, so this bowl is going to be, maybe it's like a, I guess maybe it's more like a cup. I guess this should have been a cup. That's kind of funny. Anyways, here's our bowl. Now, in particular, let's identify the volume and our surface area, and we'll use those to solve our problem. So in particular, if our height is h, and if our radius of the circle is r, then what is our volume? What's our volume? Yeah.
Pi r squared h.
Very good.
The area of the circle times the height.
Very good. The area of the circle, which gives us our top face, multiplied by all of that region, so we're multiplying by the height here. What about our surface area? So our surface area, we're going to need to add one copy of our circle because we're only looking at a bottom face, times the area of that rectangle which wraps around the cylinder. So in this case, this is going to be this blue region right here, which is going to have area, the circumference, times height, plus the yellow area, pi r squared. Okay, so we're given that the area must be 4,000 centimeters squared. So here, which one is our constraint? Is A our constraint or is V our constraint? A is our constraint, so we use that constraint to sub back into our objective function and to make the objective function a single variable function. So now we need to isolate A in terms of either H or R. Who likes completing the square? Who does not like completing the square? Okay, so instead of completing the square, see, originally I wanted to isolate for R, but no, we're going to isolate for H. So H is equal to 4,000 minus pi r squared over 2 pi RH. Oh, over 2 pi r, excuse me. I made that same mistake last time. Here, we can substitute them into each other to get v as a function only of r. So v of r is equal to pi r squared times 4,000 minus pi r squared over 2 pi r. So is everyone okay with how we converted our constraint and our objective function into a single variable objective function? Aha! So now we know how to use calculus on this function here. In particular, well, let's actually rewrite our function v. So we'll cancel our pi and our r. So this turns into r times 4,000 minus, let's pull the 1/2 to the front. 1/2 r times 4,000 minus pi r squared. In this case, the derivative of v is v prime of r, which is take product rule 1/2 4,000 minus pi r squared plus 1/2 r times negative 2 pi r. Alrighty. So if we set this equal to 0, we'll multiply both sides by 2. So we get 4,000 minus pi r squared. Or 2, so we get minus 2 times 2, those cancel. 2 pi r squared equals 0. So this is 4,000 is equal to 3 pi r squared. So r is equal to the root. So r is equal to the square root of 4,000 over 3 pi. And we do not need a plus minus because a negative r will give us, well, it doesn't make sense. Okay, what questions do we have about this one? Oh, yes.
Is it common to get situations where a negative answer is possible?
Generally, no, I don't think so in the real world. The question was, is it possible to get an answer where a negative answer is a maximum? I don't think so. Not that I've seen. Yes. I'm sorry?
Where did the half go in front of the 4,000?
So that we multiplied both sides by 2. That arrow is multiplying both sides by 2. Okay. Let's keep going. So Michel. Oh, there you are. How's it going? Would you like a lollipop? Yes, so Michel loves making cakes. Also, you put the account where you made the post, so I took a look. It's very cool.
Did you see the math one?
Oh, I did not see the math one yet. I'll have to take another look. So thanks. So Michel loves making cakes, but for your new creation, this is a true story, right? Instead of making no, I just made this up. But instead of making a traditional cylindrical cake and cutting triangular slices, Michel creates a triangular cake in the shape of a right triangle with legs 5 inches and 9 inches. So here's our 9 inches and our 5 inches cake. And the goal is to cut a rectangular slice with the largest area. So here's our slice, and here's our cake. Okay, What is the largest such area from the top of this rectangular slice? So we're going to let this distance be x, and this distance be y. So in that case, we can write our objective function. Mitchell, what's the area of a rectangle? Yeah, so area of x and y, that's what? So there's our rectangle in blue, the slice. What's the area of that slice if our dimensions are x and y? xy, yes. So that's our area of our rectangle. So now the question is, how do we get a constraint? Yeah. Y is less than 9, x is less than 5. Yeah, we could say that. So that does give us some constraints. What we need is a single equation that relates x and y. So those just give us upper bounds and lower bounds on y and upper bounds and lower bounds on x, but they're separate from each other. We need a way we can relate x to y. Yeah.
We use the properties of similar triangles, so 9 minus y divided by x would be equal to y divided by 5 minus x.
That's pretty clever. That's a different approach than the one I was thinking. You could treat these as similar triangles. Very good. I'm going to show you an approach I like, but we'll get one more. There was another one, someone over here. Yeah.
You would put a line on a Cartesian.
Yes, that's what I was thinking. That's very good. Do we have one more back here, we said? Yes, we'll use the slope. Very good. So we're going to imagine that this triangle is on the Cartesian plane. Here's our x-axis and here's our y-axis. And in particular, we have a line that passes through the points 0, 9, and 5, 0. Now we know that this point here, our xy point, is going to lie on that line. So let's find what the equation of the line is. First, m is equal to rise over run, so 0 minus 9 over 5 minus 0. And our b we can find by reading that right off the graph. Our b is just 9 because that's our y-intercept. So our line is of the equation y is equal to negative 9 over 5x plus 9. So that is our constraint. Is everyone comfortable with that? Okay, so now that we have this constraint, let's sub it into our area formula. So a of x is going to be the function x times negative 9 over 5x plus 9. What shape does a have? Yeah, one more time? Parabola, yes. It's a downward-facing parabola, so there's a maximum at its vertex. It's actually, in fact, a global maximum. So we'll compute the derivative and locate that vertex. So a prime of x is equal to 1 times negative 9 over 5x plus 9 plus x times negative 9 over 5. That's from our product rule. If we set this equal to 0, we'll have that 9 is equal to 2 times 9 over 5x. So in that case, x is equal to 5 over 2. Now the question says, what is the largest such area of this rectangular slice? We're going to now sub this optimal value of x back into a. So a at 5 over 2 is equal to 5 over 2 times negative 9 over 5 times 5 over 2 plus 9. And that is our final answer. By the way, so we're going to take a quick pause. We did 4 optimization problems today. 3 of them correspond almost exactly to your 3 optimization problems on your child's math. So refer back to these. Make sure we're setting up, we're modeling our equations, we're identifying the objective function, substituting our constraints to get a single variable function, and then maximizing that single variable function. So is everyone okay if we shut the door on optimization for now? Very good. So let's talk about reversing derivatives. So in particular, this whole course, we've been talking about finding the derivative. We're given a function f, find its derivative. Now, we're going to start talking about how it works to reverse a derivative. So we'll let f prime be equal to x cubed minus x plus e to the x. Our goal is to find f. So in particular, we want to find a function such that when we take its derivative, we get back f prime. Okay, let's do this term by term. So, what function, let's start with e to the x. What function, when you take its derivative, gives you e to the x? Yeah. E to the x, very good. The exponential function is its own derivative. So this is e to the x. Now, in order to get a power rule on taking or like an inverse power rule, we'll remember our original power rule, the derivative of x to the n is equal to x to the n minus 1 times n. So if we divide both sides, we'll get that the derivative, so x to the n minus 1 is equal to the derivative of 1 over n x to the n. So we're going to use that up here. In particular, when n is 3 here, we have, so when n is, or sorry, when n minus 1 is 3, actually let's re-index. One more step, re-index. That means that x to the n is the derivative of 1 over n plus 1 to the power of x plus n plus 1. So in that case, we'll sub this in over here. We'll add 1 to our power, which turns into x to the power of 4, and divide by that new power. And we'll do the same thing with our x. So 1/2 x squared. And the only thing that we might want to do, a sanity check, is we'll take the derivative and see if we get f prime back. So if we take the derivative, we'll get 1/4 times 4x to the 3 minus 1/2 times 2x squared plus e to the x, which is exactly the original function we had. So I have one more question. Our solution here, f, is that complete? Are we done yet? No. What do we have to, what should we not forget? The plus c, yes, very good. So never forget the plus c. Remember, a function does not have only one antiderivative. In fact, it has infinitely many antiderivatives. The antiderivatives of a function f realize a class, a family of functions, and that is going to be something we're going to study more in 1ZB3 when we talk about differential equations. But we can ignore that for now. We're just going to look at more antiderivatives. So this is homework. Guys, I put like 7 questions on here of these. This is homework. This is the one we're going to do next. So, oh no, this one's homework. Here we go. This is the one we're going to do next. So we'll let f prime equal 1 plus x squared over x to the 4. Let's find f of 2. Okay. I'll give you guys a sec to try this one on your own. And in the meantime, who wants lollipops? All right, I'm going to give you, Eddie, I'm going to give you a big, can you hand some around to people, everyone nearby? I give you a handful. Can you give those to people nearby? Here you go. Here you go.
Thank you.
Very good. I'm going to toss you a couple, okay? Can you catch, here, catch. A couple more? There. Send those over there. So we'll get a couple here. Here we go. Here, do you want to, here. Alrighty. Here you go. Pass some of those down. Oh, we have 5 of you guys. All right, here. Have some more. Here we go. There you go. You. Yeah. Thank you for participating. Here we go. You got some over here, 4. And then, here we go. 3 over here. Oh, I'm so sorry. Here we, oh, I'm sorry about that one. Here. I'll give you a new one. Oh, I did that again.
I'll take the ground one.
You'll take the ground one? You sure? All right, here we go. Here you go. Okie dokie. So, okay, so, here you go. So, Okay, oh, here we go. Okay, so, good catch. Okay, so if you, oh, okay, I'll come around over here. Okay. So, here we go. Here, take a couple for you guys. Oh, yeah, here. There you go. Here.
Oh my god.
Here you go. I'm just gonna, those are for you guys. Okay, oh. Can I say, oh, fine. Okay, here we go. So everyone, can I also, I forgot to say, please take your garbage with you. I remember a couple years ago, the first time I TA'd this course was when I was, well, this was 2 years ago. I brought candy for everyone on the first week, and then everyone left their garbage there, so I had to go back and clean it up. So, anyways, take it with you, and there will continue to be candy.
Thank you.
There you go. Alrighty, so let's get back into this problem here. So we'll take the antiderivative in this case. Who got an answer for this one amidst all of that chaos? Answers? Yes, what did you get? Negative 13 over 24. X? Oh, f of 2, I forgot. Okay, I don't think I finished this question in the last tutorial then. Oops, that's okay. So we'll take this antiderivative. The first step is that we have to take out that x to the 4. So we'll expand this into our fractions here. This is going to give us 1 over x to the 4 plus 1 over x squared. In particular, now we can write this as x to the negative 4 plus x to the negative 2. So when we find f, we're going to use our inverse power rule again. So we'll add 1 to the power and divide by the new power. So we'll add 1 to the power and divide by the new power. And we don't forget the... Okay, very good. Then we need more energy than that, guys. And we don't forget the... Very good. Okay. So we've solved this one. Does anyone have any questions about taking this antiderivative? Yes? Oh, yeah, I'm like exhausted, guys. Sorry, okay. That's pretty good. Who said that? Oh, that's hilarious. Did you get a lollipop? Okay, good. Very good. Alrighty, so f of 0 is 0. Oh, what the heck? This is not possible because... Okay, this is dumb. So, okay, so this is definitely not possible because if f of 0 is 0, how do we find f of 0? Well, that means we have to divide by 0. So this is definitely a silly question. So just ignore that part, and this is f of x. You know what's funny? You know how I have all 7 of those? This is one of the ones I didn't solve last year. I think I... Anyways, so that's silly, but let's just ignore that. Alrighty. This is another good one. This is homework. Oh, guys, what's the antiderivative of this one? Yes, arc sine, very good. And then you just plug it in. So here, let's just, you know what, let's just do this really quick. So f of x is 4 arc sine of x plus c. So f of 0 is 0 plus c, which is equal to 3. So f of x is equal to 4 arc sine of x plus 3. So f of 1 over root 2 is equal to 4 times arc sine of 1 over root 2. Does anyone know what the arc sine of 1 over root 2 is? Yes, very good. Plus 3. So it's 4 times pi over 4 plus 3, which is pi plus 3. So that's like 6. I'm joking. That was another joke, but it's okay. Okay. Gauss's trick. All right, we didn't get to this in the last tutorial. I'm actually glad we're moving a lot quicker time-wise. Am I going too fast this tutorial? Is that, no? Okay, this is good. So, Gauss's trick. So, the story behind this one is Alrighty. Alrighty. Let's reconvene. So the story behind this one Gauss's trick is apparently this happened to a young Gauss when he was asked to add up numbers from 1 up to something. He came up with this formula. Is anyone curious why this formula works? When we have this 1 plus 2 plus, yeah, you're curious? So let me see if I can remind myself how this works actually. So we have this, right? So if our goal is to compute, let's call it S. S is 1 plus 2 plus ... plus n, right? So if we add S to itself, 2S is equal to 1 plus 2 plus ... plus n, and then we need to add it again, right? So let's do it in reverse. We'll do it n plus n minus 1 plus ... plus 1. So we'll add this together here, S plus S. So 2S is equal to n plus 1 plus n plus 1. Is everyone okay with this so far? So what we're doing is we're adding them to each other, but we're adding them in reverse order. So when we add n and 1 together, that's n plus 1. When we add 2 and n minus 1 together, that's n plus 1. All of them is n plus 1. How many copies of n plus 1 do we have? N of them. So 2s is equal to n plus 1 times n over 2. 2s is n plus 1 times n. So s is equal to n times n plus 1 over 2. So that's my proof. Also, who liked that? The people who just said I wanted to see the proof and then just was interested to see the proof. Okay, you guys should take more math courses. Who didn't like what we just did? Okay, well, okay, that's fine. Whatever. So, for those who find this interesting and want extra practice, prove these. Alrighty. So, Naomi. So Naomi was in the last tutorial. So Naomi sails on tall ships and is counting the number of islands that they spot in 1 hour. At each minute I, they spot I minus 1 cubed islands. How many are there total? So we want to compute this sum of I is equal to 1 up to I minus 1 cubed. Does anyone remember? Okay, I actually I did this question in like 2 minutes in the last tutorial. So it's good that we have time to talk about it. Does anyone remember the binomial expansion? Yeah. So what is so could you tell me in the back, what is I minus 1 cubed? That's correct, but can you tell me what is I minus 1 cubed? Sorry? That's okay. Who wants to try? What's I minus 1 cubed? Yes, over the back.
I cubed minus 3i squared plus 3i minus 1.
Very good. Nice. So this is the sum of I is equal to 1 to 60 of I cubed minus 3i squared plus 3i minus 1. So if we distribute this sum across our function here, this is the sum from I is equal to 60 of I cubed minus 3 times the sum from I is equal to 1 up to 60 of I squared plus 3 times the sum from I is equal to 1 up to 60 of I minus what happens when you add the number 1 60 times? It's 60. Alrighty, so all we're going to do is use our Gauss's trick formula with n equal to 60. So here, this gives us our left term is going to be 60 times 61 over 2 squared minus 3 times 60 times 61 times 121 over 6 plus 3 times 60 times 61 over 2 minus 60, and that is our final answer. Okay. By the way, who's annoyed that I'm leaving my final answer like this? Okay, here's why you shouldn't be annoyed. In most of your child's math questions, you can substitute large expressions like this one. So once you're done with all your calculus, just plug that in. No need to lose marks by simplifying and making mistakes. So this is fine. But let's say you're still angry at me, and you want me to simplify this. I want to solve this question in a second way. How are we going to solve this in a second way? Does anyone know this? Especially if you're in computer science, this is a very good trick. Instead of making my for loop run from 1 up to 60, let's make my for loop run from 0 up to 59. I'll show you what I mean. Let's set m equal to I minus 1. So if I is equal to 1, then m is equal to 0. And if I is equal to 60, then m is 59. So my sum is equal to the sum from m is equal to 0 up to 59 of m cubed. So this is just, we plug in the Gauss's trick formula. This is just 59 times 60 times 119 over, oh, no, that's not correct. This is just 59 times 60 over 2 squared. So now, we just proved that these two numbers are equal. Okay, so is this slightly more satisfying of an answer? Okay, so my homework for you is also to plug in those two numbers into your calculator and verify they're equal. All right, so next week is Halloween. Wear your costumes. There's going to be chocolate. And we're going to talk more about summation and integration. Thank you very much. Hey, welcome back. Thank you for waiting, for coming back for another tutorial here.
I usually watch this twice because I low-key always fall asleep during the actual calculus
Oh.
thing. So this is how I get all my calculus done.
That's fair.
You started to bring up more methods to I'm just kind of really
The first thing I would say is, can we set this up on the Cartesian plane?
Yeah.
So our triangle is going to lie on the variables x and y. Yep.
I'm going to get it straightened out.
Okay, so on our Cartesian plane, so here, this is our triangle, this is x, this is, no, sorry. How do you erase?
Just scribble.
Okay, very good. So this is our rectangle, this is x, and this is y, right? So we want to find a relationship between x and y. This line is our relationship between x and y. X and y will always be on this line, right? So we can relate them to each other by finding out what this line actually is. So what is this line? Well, this line goes through the points 0, 9, and it also goes through the points 5, 0. So let's find an equation for this line. How do you find an equation for this line? Let's find the slope first. So what's the slope of the line?
9 minus 0. Oh, wait, no.
Yep, that's correct.
Just 9 minus 0, 0 minus 5?
Yep. So it's negative 9 over 5. And what's the y-intercept?
9.
Yep. So now we get that the y